See how many minutes I've taken to talk about this issue. I mean, no lecturer takes delight in seeing students absenting themselves. At the end of the day, it's the two of us, students and lecturers. We need to work together. But if you decide not to come to class, who should I come and teach? Huh? Who should I come and teach? At the end of the day, you're also going to be assessed. And like I said, I personally don't take delight in failing students, even when you deserve it. You see? So come and let's all work together and make a progress. But you stay away and then you get F, and then you come and bother us with emails and calls and those stuffs. Let me see, let me see if I can capture participants. Sit in the chat room. I'll be with you shortly. Just want to see in the quiz, and they can take me to wherever they want to take me to.
Okay, no.
All right, Leonie, where did we get to the last time? I think I asked somebody to note it down.
Gifty.
Hey, Gifty.
Yes, sir.
Why is your voice like that? Are you sleepy?
No.
What's wrong?
I'm sad.
About what?
You
About what?
blasted us this morning.
What has happened this morning?
I'm saying you blasted us this morning.
Oh, I blasted you.
As in all of us.
Hey, but no, I've not blasted you. I'm only trying to express my dissatisfaction with the attitude some of you are showing. You see, is that what you do on the other courses?
No.
No.
So I think the problem is we need to know the real number of students.
That's what I've given.
Yes.
That's what I've given you. You are over 36, between 36 and 40.
Oh, okay.
That's what I have noted. But if it's more than that, I don't know. I've requested for the list. I'll get it maybe by the end of this lecture, I'll get it. Then I'll know the real number of students in group 1. Then I can take proper action.
Yes, please. Okay, so please, we go to page 234.
Oh, I thought it's slide 235, isn't it? Yeah.
Yes,
Have
so
I
we are
shared?
starting from 235.
Okay. Can you see my my share screen, Gifty?
Yes, please.
Okay. You are Gifty what?
I'm Gifty to say.
Gifty too. Okay.
Yes, please.
People should come, so I chop teacher on you. You people don't want to come. Hello, Sandra. Hello. Okay. So we are starting, what is the name? Designing production layout, product layouts. We said we arrange machines or workers in a line according to the operations that need to be performed to assemble a particular product. Then we break jobs into their smallest indivisible portions. Then we group. Yeah. 1 minute. Class, I'll be with you shortly. It's okay. It's all right. Which one?
Foundations of Performance.
Yes. So I spoke to, you sent it, yes. Yes, when we had a conversation. Yeah. So I told Roger that I was going to print it this morning. Yeah, yesterday it didn't work. So this morning when I came, I tried. I also tried with Dr. What's it? He came here, the one who takes financial accounting, Dr. Sapon. Okay. Yes, we tried. It blurs it out. Okay. It prints and then blurs the copy. Okay. So we have to use the number 13. Okay. So my plan was that if after my class you are not in, I will go and then do it.
I was actually somewhere. I had to, because he didn't tell me like he had gotten you, and I sent you a text. I didn't hear anything, so I had to rush.
Sorry about this.
Run. I'm sure you were in the class. So
yes, I would have sent you a text. Oh dear. I'm even getting calls, but I'm not picking them.
I know you're in the class. Sorry.
So you need to pray. Did you come with a copy?
No. It's the email, because I sent it to him.
Okay, then let's ask Roger to print out the copy for you.
Okay, I can easily just bring it.
Okay.
Should I print so that you run?
Yes, when I finish, I'll go and run it for you.
Okay.
Thank you. Okay, thank you. Class, sorry for the interruption. Gifty, where did I get to?
Hello, sir. Please, you were just about starting.
Okay, so we are talking about designing product layouts. Oh, who is this? Arrange machines or workers in a line according to the operations that need to be performed to assemble a particular product. We break jobs into their smallest indivisible portions. That is what we call work elements. We group the work elements into workstations for smooth flow of products. And then we should also note that every workstation requires at least one worker or one machine. And in doing so, we also need to make sure that precedent requirements are adhered to. Precedent requirements are adhered to. Once again, let me bring in our usual hairdresser salon as an example. So if you look at the hairdresser salon, there are jobs or tasks that have been grouped into workstations. And here, when we say that we arrange machines or workers in line, it doesn't necessarily mean that the line should be a straight line. Being in line can be a U shape. But what is important is that there is that sequential flow of activities. So the product will move from one stage on the line to the other. So being in line can be a circle shape, it can be a U shape, it can be L shape, as long as there is that sequential flow of activities. Is that understood?
Yes, sir.
Okay. So coming back to the hairdresser salon, you see that you have jobs which are broken down, and the jobs which are broken down and are then put into workstations. As usual, we have identified three different workstations within the hairdresser salon. And the first workstation is where the washing is done. And if you look at where the washing is done, we have two tasks there. What are those two tasks? We apply the cream to the hair, and then the client or customer sits down for a while, and after a while, the cream is washed off the hair. So two set of activities in there. Then from there, the person moves on to the next workstation. The next workstation involves the client going to sit under the dryer for some number of minutes. 30 minutes or thereabout. Then when the hair is dried, we move on to the next workstation. Francis, I'm in the printing room.
Okay, all right.
After that, the person moves to the styling stage where the hair is styled, So you can see that the jobs have been broken down and into smaller bits and combined in terms of workstations. And that's a typical example, illustration of the concept we are learning today. So those indivisible jobs or tasks, the smallest portion of the jobs that organizations are able to identify, we call those ones work elements. And then we group these work elements. So in my hairdresser salon example, the work element in workstation 1 will be the application of the cream to the hair. Another work element will be washing of the cream from the hair. So two work elements. I mean, you cannot break that job down any further. I can't see how you can break down the application of the cream to the hair any further. So that is the smallest. And every workstation should require at least one worker and one machine. Or one machine, not one worker and one machine. One worker or one machine. So again, using our hairdresser salon, workstation 1, does it have a machine or it has a worker?
Hope it's a worker.
Sorry?
It's a worker.
It has a worker. Workstation 2?
Machine.
Machine. Workstation 3?
Worker and machine.
Okay. Normally when you are styling your hair, does that require machine?
Yeah, at times they use some machines to do it.
Okay, so worker and machine, great, great. Okay, then we talked about precedence requirement. Is this the first time you are coming across this word precedence? Have we come across it in the course of the lectures?
Yes.
Where? Where?
We are doing the design.
This one. You are talking in a class. Raise your voice a little. Or you are at work, so you can't talk louder.
Yes, I'm at the lecture hall.
Hey, right there.
I'm at the lecture hall.
You are the lecture hall. Are you? Anyway,
I'm at the business school lecture hall.
lecture hall where?
Graduates. So,
You are attending a different lecture?
I'm having my online test now. So please, I'm having my online lectures here
Ah, okay.
because of the
Okay.
network.
Okay. And there are other people in the room.
Yes, a little.
Okay. So can each workstation take the same amount of time to perform the work element assigned to it? If yes, no work will be idle and no product will have to wait. But in reality, that is often not the case. Can each workstation take the same amount of time to perform the work element assigned to it? Let's come back to our hairdresser salon. Now, Leonie, since you are regular at the hairdresser salon, roughly how many minutes does it take to go through the first stage, application of the cream and washing the cream of the hair? Roughly how many minutes can that take?
So it depends because I don't apply cream on my hair. I keep brushing hair, so mine is natural.
You haven't done that before?
No, I've done it, but I think
Okay, so let's go back to the days when you do it. Roughly about 10 minutes, 20 minutes?
yeah, 5 to 15 minutes, depending on the scalp of the client's hair.
Okay, so 5 to 15 minutes. And then when you sit under the dryer?
At 15 to 30 minutes, depending
15 to
on
30,
the
depending on how efficient the machine is, isn't it?
how coarse the hair is as well.
Okay, and how coarse the hair is as well. Thank you. So the point here is that each workstation we can't arrange it in such a way that each workstation will take the same amount of time to do the work. And again, even apportioning of the work to the various workstations is another issue. Can we apportion the same workload to each workstation? You see? So these are often the challenges in reality. And that is why this concept of balancing the assembly line comes in, which we are going to look at today. Okay? So in doing the layout, our objective is to try and balance the assembly line. Balancing the assembly line is that we don't want a workstation to be overloaded. Remember what we learned last week about bottleneck. If one workstation is overloaded with work, it becomes a bottleneck. It constrains the whole operations process and it leads to delay. So the objective here is that let's try and balance the assembly line, making sure that there is relatively the same workload assigned to each workstation so that a workstation doesn't become overloaded whilst others are sitting down and playing with their phones. Okay? The objective is to balance the assembly line, equalizing the amount of work at each workstation. Okay, let me point out here that, yes, even though that is the objective, we can still not assign equal portion of work. Whatever the case may be, Yes, we may attempt, but we can't get it all equal, as you will soon see. Then we need to draw what we need when we are assigning the work to workstations. We need to look at our precedent requirements, and the precedent requirements is in the form of diagrams. Precedence here we are talking about which work, which job must be done before which work, or which job, which task must be completed before which task. Okay, so let's say we have 3 tasks, task A, B, and C. And task B depends on task A, and task C depends on task B. We can only do task C when task B is completed. And we can only do task B when task A is completed. That becomes the precedent. So B precedes C and A precedes B. That understanding is very, very important to enable you draw the what we call the precedence diagram. Then we also need to calculate what we call the cycle time. And the cycle time is the maximum amount of time the product is allowed to spend at each workstation. So because the idea is for us to balance the assembly line, try and ensure that there is relatively the same amount of work spread across the assembly line, then it also means that the amount of time spent at each workstation should also be regulated if we want to balance the line. So the cycle time enables us to calculate, determine the amount of time, the maximum amount of time that when a job gets to a workstation, it should spend. And a job is not allowed to exceed that amount of time, what we call the cycle time. Now, how do we determine that cycle time? It is the production time available divided by the desired number of units. So let's say in a typical 8-hour day, we are required to produce 10,000 units of bottled water. 10,000 units of bottled water. What will be our cycle time? What will be our cycle time, class?
Please come again.
I said in a typical 8-hour day, we are required to produce 10,000 units of bottled water. What will be our cycle time?
0.0008.
0.00. How did you get that? Production time available?
Yes, over the desired output, which is 10,000.
Yes, so that's how we calculate our cycle time. And the determination of the cycle time is very, very important to enable us balance the assembly line. Like I said, the cycle time is the maximum amount of time that the product should spend at each workstation. So coming back to our hairdresser salon, if the cycle time has been calculated to be, say, 10 minutes, then when the client first gets to the workstation 1, where the cream will be applied and the hair will be washed, the operator there must not spend more than 10 minutes. Then it moves on to the next stage. When the client gets to the second stage where the drying will be done, the machine should be efficient enough to do the work within 10 minutes. And then it moves on to the styling stage where the same maximum. But you see, you cannot exceed. Now your hand is up. What is your question?
Yes, I was going to ask, is there any allowance for errors in calculating this?
Errors.
Yes. So let's say we know, as we are saying, it shouldn't exceed. But what if for some reason the machine took a while to start, there was network issues and stuff like that? Is there any way we can allow like room for these things?
Okay, so this is where we hold other things constant. Okay, so if the machine breaks down, we know the machine has broken down, so we need to fix the machine. But if the machine is fixed and everything becomes normalized and we're operating, this is how much time the product should spend at each workstation. Is it answered?
Yes,
Also not
please.
true. Okay, thank you now. Okay, so the first one is the flow time, which can also be referred to as the lead time. And this is the time required to complete an item. This is the time required to complete an item. Once again, let's come to our hairdresser's salon. Now, if at the workstation 1, it takes 10 minutes. The flow time, it takes 10 minutes. Workstation 2, where the drying is done, also 10 minutes. Workstation 3, where the styling is done, it also takes 10 minutes. So if a client or a customer enters the facility, within how many minutes do we expect that the customer will walk out of the facility?
30 minutes.
30 minutes. 30 minutes. And that is what we refer to as the flow time. Flow time. Flow time. Then we have the actual cycle time. Actual cycle time is the maximum workstation time on the line. You see, please don't get the difference between the C sub A or CA and the CD. They are not the same, this CD. We'll see how both are calculated. The CD is the maximum amount of time that a product is allowed to spend at each workstation. But you see, when we group the work elements into workstations, it is not really possible to have work elements with the same timing. So in one workstation, even though the CD is 10 minutes, the work elements we are combining into workstation 1, we may end up getting like 9 minutes. Workstation 2, even though the CD, the cycle time is again 10 minutes, we may end up, the work element that is supposed to be done there, we may end up getting like 8 minutes. Then workstation 3, even though the cycle time is 10 minutes, we may actually be spending like 8.5 minutes. So with these different timings, the maximum amount of time, actual time which is spent, you know, the CD is not the actual time which is spent. Hello, class?
Yes.
Yes, sir.
A CD is not the actual time. The
Yes,
CD is a theoretical time we have calculated per so and so per the work element times and everything. Every workstation, we shouldn't spend more than 10 minutes. So that is not the actual time. But when we combine the work elements and the actual work is being done, we will have different timings at the different workstations. So some can be 9, some can be 8, some can be 8.5. Now, the maximum actual workstation time, in the example I gave you 9 for workstation 1, 8 for workstation 2, 8.5 for workstation 3. The maximum here is 9. So the 9 becomes our actual cycle time. Class, is that clear?
Yes, sir.
Yes, please. Then another terminology that we need to understand is what we call the balance delay. And the balance delay is actually the total idle time. The total idle time. Now let's come back to our hairdresser salon again. We have 3 workstations. What is a CD? Our assumed CD.
It was 0.00.
No. Our assumed CD here is 10 minutes. Our assumed cycle time for the
Yeah, it was 10 minutes.
The line for the salon is 10 minutes.
Yeah.
So we calculated our flow time. The flow time we said is the total amount of time the product will spend from the beginning to the end. So when a customer enters from workstation 1, 10 minutes, workstation 2, 10 minutes, workstation 3, 10 minutes. So we expect that in 30 minutes, the customer is going to walk out. Then we say the actual time which is being spent, even though the cycle time is 10 minutes per workstation, the actual time which is spent on the workstations are these. That workstation 1, the actual time is 9, workstation 2, the actual time is 8 minutes, and workstation 3, the actual time is 8.5 minutes. Out of these 3, the maximum time there, actual time is 9 minutes, and that is our actual cycle time, which is the CA. Now we are coming to the balance delay, which is the idle time on the line. Idle time on the line. The idle time on the line. What is our total CD?
30
minutes.
Our total time on the line is supposed to be 30 minutes. In practice or in reality, how much time are we spending?
25.5.
It's 9 plus 8 plus 8. So 25.5. Yeah?
Yes, bro.
So roughly we are, the idle time on the line is going to be what?
4.5.
4.5 minutes. 4.5 minutes. But usually this is calculated in percentages. So we'll look at it as we go on. You look at efficiency, you calculate the efficiency on the line, and then you subtract the efficiency from 1. You look at the efficiency on the line, and then you subtract that from 1, and that will give you the idle time on the line. The idle time on the line. Here you go. All right. So where do we start from? Balancing the assembly line process. We start from step 1 up to 6. What do we do in step 1? We draw and we label our precedence diagram. Now the precedence diagram shows us the sequence and the flow of the activities on the assembly line. It tells us which activities we do before which activities. It tells us the relationship that exists between the activities. We get to know from the precedence diagram which activities come first before which ones. Now, when we draw our precedence diagram, the step 2 is for us to calculate the desired cycle time. Thank you. The desired. 2 participants have raised their hand. Yes, go ahead. What's the issue?
Yeah, hello, sir.
Yes, sir. Carry on.
I wanted to ask if the precedence diagram is the same as the flow chart or the flow diagram.
The precedence diagram.
Yes, is it the same as the flow diagram?
The flow chart, which we saw earlier on, is different from the precedence diagram.
Okay, thank you.
But the understanding may be related. Let's see an example of the precedence diagram, then you may understand it better. Now, Moko, what's your question? Now, Mili. Now, Shoko. Now your hand is up.
I believe it's her old hand.
Okay. Okay. Thank you. So we draw and we label our precedence diagram. We calculate the desired cycle time, which we already know the formula. What's the formula for calculating the desired cycle time?
The production time available over the
production time available divided by the desired output level. Okay. Then we go ahead and then we calculate the theoretical minimum number of workstations. We use the cycle time to determine how many workstations we should have on the assembly line. And then we group work elements into workstations. And when we are grouping work elements into workstations, we must respect the cycle time and precedence diagram. You see? Or we must respect the cycle time and precedence constraints. Now, what do we mean by respecting the cycle time if we are grouping work elements? What do we mean? Okay, since you don't, nobody knows.
Sir,
Go
please,
ahead, try. Good.
Okay, sir. So if you want to, you need to consider the time, because when you pipe up most of the work at one workstation, it might exceed the time.
Yes, respecting cycle time here simply means that if you have calculated your cycle time to be 10 minutes, and there is a work element which takes 5 minutes to do, there is another work element which takes 6 minutes to do. If you put these two together as two activities to be done in one workstation, you have exceeded the cycle time of 10 minutes, and that is not allowed. So whichever work elements you are combining, make sure that the timings for those work elements are within or up to the 10 minutes. You cannot go beyond the 10 minutes. And this is why we are saying that you must respect the cycle time. And then again, you should also respect the precedence constraint. So earlier when I gave you an example that we have 3 activities, A, B, and C. And that C depends on B and B depends on A. So if we are going to combine work elements, there is no way we can combine A and C to be done in one workstation. Why can't we combine A and C?
Because B must be done before C.
Perfect. Because B must be done before C. So if you go and add A to C, at that point, B has not been done, so we can't do C. So this must guide you when you are doing working out your workstations. Then point 5, we calculate the efficiency of the line. We'll see that in the next slide. We calculate the efficiency of the line. Just understand the formula, okay? Don't chew them. At this level, we don't want to encourage you chewing the formula. If you are familiar with it, fine. Yes, you have to be familiar with it so that when you see it somewhere, you can recognize it. I keep telling you that in the exams, at the back of your question paper, all the formula you need for each of the questions on the paper will be there. So you don't have to bother yourself. But if you are not familiar with it, even though it is there, you can't see it. And then we determine if N or acceptable E has been reached. N is the theoretical number of workstations. If not, we go back to step 4, and then we go through the rest of the process again. Class, up to this point, any question? No question. Okay.
Doc, please, can you go over the 6 again?
The 6 is that determine if acceptable N. Acceptable N is the number of workstations.
Okay, sir.
So determine if N or acceptable E has been reached. And if not, we go back to step 4 and we'll do the grouping. You see, let me explain this to you. Say if you have calculated the design cycle time, the maximum amount of time that the product should spend at each workstation, you have calculated that to be 10 minutes. And then at some workstations, the work elements you have there, they are spending just like 3 minutes. You go to another, they are spending just like 4 minutes. It means that you haven't been able to calculate the theoretical number of workstations well. And that's why there is so much time being wasted. So the work elements that you combine to be placed in workstations, the actual time that these work elements will consume should be as close as possible to the design cycle time. The only constraint is that you can't exceed the design cycle time, but it should be as close as possible. When you leave so much allowance, then there is going to be a lot of idle time. Okay. So let's go to a typical example. So this is the formula for, now what is the big N? Now, what's the big N?
Hi, the workstations.
The workstations, the theoretical number of workstations.
Yes,
Theoretical number of workstations. So what we do here is that we sum up the work element times. We sum up the work element times, and then we divide that by the desired cycle time. Yeah? Class, 1 minute. Today I'm multitasking. Yes, sir. Yes, sir. Okay. Yeah. Please, when you are done, bring it to me. Okay. So this is summation of the work element time divided by CD. What is a CD?
Design cycle time.
Design cycle time. And to determine the efficiency of the line, we sum up the work element times. Work element, if you say work element time, what we are saying is that the specific task, each will have time requirements. So if there are about 6 tasks there, each of them will have the time requirements, say 1 minute, 3 minutes, 4 minutes, or 10 seconds, 20 seconds, 30 seconds. So whatever timings you have for each of the work elements, you will sum them up. You will sum them up, and then you divide it by N. N is the number of workstations you have. So before you can determine the efficiency of the line, you need to calculate the theoretical number of workstations first. You can't do this when you have not done this. So we need the number of workstations. And then this is the CA, the actual cycle time. And how did I explain the actual cycle time, if you remember? How did I explain the actual cycle time?
The actual minute that it takes to complete the activities.
The maximum time, yes, on the shop floor that it takes to complete an activity. Okay. Okay. Gifty. Today you are my darling, so let's go.
Okay, so we have facility layout.
Yes.
So suppose a company has 3 station assembly line shown below. If the company wanted to produce 120 units in an 8-hour day, the cycle time necessary to achieve the production quota is 4 minutes. However, flow time will be 12 minutes, since to get a finished product will require spending 4 minutes at each of the 3 workstations. So below are the time spent.
Okay, so class, we know how to calculate the cycle time already. The CD, cycle time, design cycle time, you can choose to call it that. We said the production time available divided by the desired level of output. Now, in this our case, what is the production time available?
Say 4 minutes.
Convert this 8 hours to minutes. What would you get? Convert the 8 hours to minutes. What would you get?
4,000. Hey.
Not up to 4,000.
480. Sorry.
480 minutes.
Yeah.
What is our desired level of output?
120 units.
120. So how do we determine our CD? It's 480, which is the production time available. 480 divided by 120. Do that
That's 4
calculation
minutes.
again,
4.
which is
4
4 minutes.
minutes.
Now,
Yeah.
what that 4 minutes is that here we are spending 4 minutes. Here we are spending 4 minutes. Here we are spending 4 minutes. Or in simple terms, the CD is the maximum time that the product is required to spend at each workstation. But like I said, in reality, the time that the product will spend in there can be less than 4 or exactly 4. Okay? Our flow time. So if the product enters from workstation 1, in how many minutes do we expect it to come out?
12 minutes.
12 minutes. And that is because it was maximum 4 minutes here, 4 minutes there, 4 minutes there. So in 12 minutes, I expect Leonie to come out with her hair styled. Then the cycle time, which is the maximum time. In this our example, we see 444. So the maximum time is 4. But in other examples, which we'll soon look at, it will differ. Okay, let's work this out. Gifty?
Yes, sir.
Let's Gifty O2. Let's go.
All right, so the real fruit snack strips are made from a mixture of dried fruits, food coloring, preservatives, and glucose. The mixture is pressed out into a thin sheet, imprinted with various shapes, rolled and packaged. The precedence and time requirements for each step in the assembly process are given below. To meet demand, Real Fruit needs to produce 6,000 fruit strips every 40-hour week. Design an assembly line with the fewest number of workstations that will achieve the production quota without violating precedence constraints. So below we have the work elements, precedence and time. So for A, pressed out sheet of fruits is 0 and the time is 0.1 minutes. B, cut into strips, precedence is A, time is 0.2. C, outline fan shapes, precedence is A, time is 0.4. D, roll up and package, that is B and C, and the time is 0.3.
Okay, now let me give you a guide. You know, typically in exams, we want to see which of you can think better. So we'll give you this. Over here, you can see it's in minutes. Agreed?
Yes, sir.
Over here, we can see it's in
hours.
So if this is in minutes, try and convert this to be in minutes as well, to make it easier for you. I'm not saying that if you don't convert it, you'll not get it, but to make it easier for you in the calculation process. Okay. Now, if we go back to the steps that we need to follow, we said we draw and we label the precedence diagram. I haven't taken you through that yet, but at least we know how to calculate the cycle time. We know how to calculate the work, what is the name? The minimum number of workstations. Let's jump the gun. what I've taught you, let's quickly do it before we see the actual calculation on the next line. Okay, so from the data here, what would be our cycle time?
2.5.
Sorry?
I had 2.5.
Your cycle time to be 2.5.
The cycle time,
The desired cycle time.
yeah, I had 2.5.
How did you do that?
6,000 divided, sorry. Ouch, okay, that's right.
Uh-huh.
0.4.
0.4.
Great. The 0.4 is correct. How did you do it?
2,400 divided by 6,000.
How did you get a 2,400?
40 times 60.
Times 60. And if you multiply 40 by 60, what are you trying to do? You are trying to convert the 40 hours into
Minutes.
Into minutes. So that will give you 4624, 2,400 minutes. 400 minutes. That's what you get. And then our desired output level is 6,000. Our know CD is the time available divided by the desired output level. So the time available is 2,400 divided by 6,000. And that gives us 0.4 minutes. Great. What does this 0.4 minutes mean? What does it mean?
It means you have to spend a maximum of 0.4 minutes per station.
Per workstation.
A workstation.
Per workstation. Okay. Now, I want us, because we've gone through how to calculate the theoretical number of workstations. Let's go back. The theoretical number of workstations, we said you have to sum up the work element times. Work element times and divide it by your CD. We have already calculated our CD to be 0.4. Now, let's calculate the theoretical number of workstations. And to do that, we first need to sum up our work element times. So let's go. Let's sum it up and see. What do you get?
7.
So N, big N, is equal to
1.0.
I'm coming. 0.1 plus 0.2 plus 0.4 plus 0.3, all divided by
0.4.
0.4. Class, are you following?
Yes, Doc.
Okay. So 0.1 plus 0.2 plus 0.4 plus 0. Will give us 1, correct?
1.
Yes,
Yes.
please.
So that would be 1 divided by 0.4.
Again,
What will be
2.5.
2.5.
2.5.
2.5. Okay. Now, in balancing the assembly line, even when you get 2.1, 2 means 2 workstations. And remember the rule on the cycle time that you cannot exceed by force. You cannot exceed the cycle time. So when you calculate your theoretical number of workstations, in this example, the theoretical number of workstations we have calculated is 2.5. But in reality, can we have 0.5 workstation?
No, please.
No, we can have 0.5 workstation. So you round it up to
3.
3 workstations. So in this case, approximately 3 workstations. We need 3 workstations. Then I also need to emphasize to you that if we have, assuming we did this calculation and we got, Leonie, your hand is up.
I wanted to ask, what if we had 2.4? Do we round it down?
That's a
Or we
good question. That is what I'm actually coming to. When we have 2.4 or even 2.1, you can run it down to 2. Because if you run it down to 2, what it means is that the jobs may go beyond the desired cycle time. So even if it's 2.1, what do we go?
We'll make it 3.
We still make it 3.
We still make it 3. Please get that understanding. If it's 2.1, we still make it 3 workstations. Because if you bring it, if you make it 2, then you may have to combine jobs that will exceed your desired cycle time into one workstation, and which is not allowed. So rather, we'll create an additional workstation. So even if you have 2.1, you go back to 3. You have 2.9, it will be 3. I hope that is well explained.
Yes, sir.
Okay. Now we can calculate this. We can calculate this. We cannot calculate this because why can't we calculate the efficiency of the line? We have done this, but we can't calculate this. Can anybody tell me why? Do we know this? Can we know this? Hello, class. Can you see my cursor?
Yes, sir.
Can we get this data?
Yes, sir. Say that one was 1.
Yes, that is a summation of the work element times. Okay. Can we get this data?
Yes.
Yes.
Which is what?
3.
Which is 3. 3, not 3.5, it's 3. Yes, 3. But we don't know the actual because we have not done the groupings. So we cannot do this yet. Thank you. Now let's move on. So as the rule says, we first have to draw the precedence diagram. So I'm going to take you through how to draw the precedence diagram. And these ones you have calculated them already, then we jump. So work element A, what is the description? We press our sheet of food. What is the precedent? Does it have a precedent? No, there is no precedent. So we'll start from A. Okay. And usually when you write, you draw a circle, put the work element in there, and you also have to put the time by the side, the time that is required to complete that work element, as you can see here. So work element A, if you go back to, it says 0.1 minutes. So as you draw the circle, you put the work element in. Sometimes it can be number 1, 2, 3, 4, 5. So you put, if it's 1, you put 1 in there, you put the work element time by the side. Doesn't matter where you put it, as long as we can identify that work element A, that is the time required to complete it. Then let's go to work element B. We cut into strips. What is the precedence? A, correct?
Yes.
And the time is 0.2. So we'll go back to our drawing, and we'll move an arrow. The arrow indicates the precedence. Don't just draw a line. In most cases, you see students drawing a line without the arrow. Now, if you draw a line, how do I know where you are pointing to? So make sure your arrow is clear. So from A to B. Then we go to, the third one, C. We outline the functions. It also depends on A, and the time is 0.4. So we go back to our diagram. C also depends on A, so we draw it. Then we go back to the data. D depends on B and C. B and C, and the work time is 0.3 minutes. So D depends on B and C. Now, in the end, this is what you are going to get with the work element time by the side. Class, this is what we call the precedence diagram. The precedence diagram. Now, if you take a look at this precedence diagram, it tells you the work element name. It tells you the direction of flow of production. that this goes here, and it meets in D. It meets up in D. This is the precedence diagram. So this is the first thing you need to do when you want to balance the assembly line. You draw this diagram. Okay. Next, we calculate the design number of workstations. I guess we understand this already. Yes, we've done this already. And please don't be jumping details. If you jump details, you lose. Maybe today I'll show you a marking scheme. When you jump details, you lose marks. For example, you see people starting from here, 0.1, or start, for example, calculate the design cycle time, and then they start from here, 2,400 divided by 600, 6,000. How do I know how you got this 2,400? It is possible that you copied from somebody and you don't even know the source of it. So don't jump details, provide every necessary detail. I realized that when I asked you to sum the work element time, quickly put it together like this, and then you gave me. But how do I know what you sum up to get what? So show me this. Okay? And I've told you that even if it's 2.1, we still need to take it to the nearest higher figure, whole figure. Okay. Now this is how, remember that we have already calculated the number of workstations to be 3. So you bring this table, workstation 1, 2, and 3, and then we assign the work elements to the workstations. How many work elements we have? We have 4, A, B, and C, and we have 3 workstations, 1, 2, and 3 over here, 3 workstations. Now, remember we said when you are assigning the work elements to the workstations, you need to obey 2 things. What are they?
The number of workstations.
You need to obey two things. What are they?
The number of workstations and the...
No, not the number of workstations. You need to obey 2 things.
Cycle time and precedence constraints.
Yes, cycle time and precedent constraints. Cycle time. In this our example, our cycle time is 0.4. So let's start. Workstation 1, we are going to assign work element A. Work element A is 0.1 minutes. So if we assign work element A to 8, we have 0.3 minutes remaining. What is work element B? What is the time? It's 0.2. But can we put these two work together? Yes, because they follow on in terms of precedence. So we'll assign work element B also to workstation 1, and we'll have 0.1 minutes remaining. We still haven't exhausted our cycle time, but can we add any more work elements?
No.
Why no? Can't we add C
No, sir.
to workstation 1 so that it should be 3 work elements in there?
No, sir.
No.
Why can't we?
Because workstation 1 has 0.4 minutes.
I haven't answered the question. Joyce Money, your hand is up.
Please, sir, can you please start again? I didn't get well you say. Thank you.
I should start again from where?
From the remaining time for element A.
Okay.
Thank you.
All right. So, Joyce, you understand this one, the number of workstations, you understand it, correct?
Yes, please.
So we have calculated our number of workstations to be 3. Now we need to group our work element. These are the work elements. These are the work elements. We need to group these work elements into our workstations. The workstations that we have calculated, the 3. Yeah? And in doing so, first we need to obey the cycle time, and 2, we need to obey precedent constraints. So we put, remember our diagram, we are starting from our precedent diagram, we are starting from activity A, work element A. Yeah. So we put work element A into workstation 1. Now, when you put work element A, what is the time required to complete work element A? It's 0.1. So when we put A into work element A, we are left with 0.3 minutes. Okay. This is where you have the confusion, eh?
Yes, yes.
Okay, that confusion is coming from the fact that for each workstation, we need to spend maximum of 0.4 minutes.
Okay.
For each of these workstations, we need to spend maximum of 0.4 minutes. So if you put a work element that spends 0.1 minutes, you have 0.3 minutes remaining. Is your question answered?
Yes, please.
Okay. Then okay, so the next activity that can be added. Oh, class, look at this. Look at this, it's beautiful. This is A is 0.1 and D is 0.3. So why don't we just add A and D as the work element in workstation 1 so that we exhaust the full 4 minutes?
Please, D doesn't depend on A.
We have to use the precedent.
Oh.
We have to obey the precedent.
That's the precedence.
Yes. And because at that point in time, work element B and C have not been done. So in workstation 1, if you give them to do, if you assign them to do the work element A and D, when B and C have not been completed. Okay, so understand that. Okay. So, but why can't we also put, because C depends on A, and so we can do C and A also together in workstation 1.
No, sir, it will exceed the maximum time needed.
Excellent. It will exceed the maximum time needed. I'm happy you are pointing out these things. I don't want to point them out to you. If you're able to recognize them yourself, then I know you understand what we are doing. Okay? So yes, even though C depends on A, and we can put A and C together in work elements, we are constrained from doing so because if we do that, the work element time for A is 0.1, work element time for C is 0.4. The two will exceed the desired cycle time of 0.4. So we are not allowed. And therefore we can only add work elements A and B together in workstation 1. And that will leave us with a remaining time of 0.1. That will be an idle time. Then we come to work, so we are done with work element 1. We can't add any more. We come to work element 2. So this and this are gone. Which work element can we put here? Can we put D here in workstation 2?
No, sir.
Why can't we?
Because we have to obey the precedence rule.
We have to obey the precedence rule. So the only one we can put here is work element C. And thank God work element C is exactly 0.4. The same as our cycle time. So we have nothing remaining, okay? And at this point, we only have work element D, which has not been assigned. This, oh, sorry, why is this computer misbehaving? At this point, we only, so if you assign, we note the ones remaining that can be assigned. Okay, so D is remaining. And then we come to workstation 3. Workstation 3, automatically it becomes just the D, and D is 0.3. So we put D in there and our time remaining is 0.1. All the work elements have been assigned. We are done, okay? After doing this, you need to draw this, the assembly line diagram. You need to draw this and tell us that this is workstation 1. This is workstation 2. This is workstation 3. Assuming you have 10 workstations, you should show the assembly line diagram showing all the workstations you have come up with. And in each workstation, tell us, Louise, I'll be with you shortly. Tell us which work elements you have combined into the workstation. And you pick that information from the table. So workstation 1, we have A and B, A comma B, that's what you have there. You put it there. And then C, you put it there. And then D, you put it element time. So A, how many minutes are required? 0.1. B, how many minutes are required? 0.3. So you see that even though the design cycle time is 0.4, the actual time which is being spent in workstation 1 is 0.3. If we go to workstation 2, what is the design cycle time? It's 0.4, correct? What is the actual time we are spending in workstation 2?
0.4.
0.4.
0.4. When we come to workstation 3, the design cycle time is 0.4. We are spending actual time of 0.3. You see? Now, if you look at what we have done, yes, even though we haven't gotten the work to be equal, we have, I mean, it's relatively, the word is relatively equal. We have tried to balance the load on the assembly line so that no workstation is having too much to do. Louis, your question, please.
So the remaining elements for workstation 1, I'm talking about the A. Why didn't we add the D? Because we have not assigned the D yet.
Why didn't we add the D?
Yes, the BC. Why didn't we add D? Since at that time we have not assigned D.
I don't get the question. Which workstation are you talking about?
So I'm talking about workstation 1, the element
Okay.
A. When you assign the A, we are left with the remaining time of 0.3. But we said that the remaining element is B and C. But at that point, we have not assigned D. So D is also remaining. Or I'm getting it wrong.
Oh, no. At that point, you see D doesn't depend on this.
Oh, okay.
Okay. Okay, so you draw the assembly line diagram as we have here. Now, at this point, can we determine our CA, our actual cycle time? Can we determine it?
Yes, bro.
Yes.
What's our actual cycle time, the CA?
Wow.
No. What's the definition for the actual cycle time? The maximum
Amount of time spent per workstation.
Come again.
The maximum amount of time spent per workstation.
And what figure is that here?
0.3.
Hey, is that the maximum?
0.4. 0.4.
0.4.
So I can see there is confusion there. I need to clarify. You see, when you put the work elements into the workstations, you need to sum up the work elements which you have put into a workstation. You need to sum up their times and write it under it, so that we know that in this workstation, this is the maximum amount of time we are spending, even though the design cycle time is 4, but we are actually spending 0.3 minutes. Workstation 2, it is taking only one work element. So, and the work element has a time of 0.4. And D is workstation 3 is only taking one work element, which is D, and the time there is 0.3. So out of these 3 timings and the workstations, which one is the maximum? Is this one, workstation 2, which is 0.4. So our CA is 4. the maximum workstation time. Please take note that in this example, coincidentally, the maximum workstation time is the same as the desired cycle time, but they are not the same. So don't always assume that, oh, the maximum workstation time is the same as the desired cycle time. Okay? Have I made myself clear?
Yes, sir.
Just a sheer coincidence that the maximum workstation time happens to be the same as our desired cycle time. In other cases, the maximum workstation time will not be the same as the desired cycle time. I'm emphasizing on that because if you get that wrong, your calculation of the efficiency of the line will be wrong. Okay, so let's go to the next. Now, efficiency of the line. If you remember the formula, the formula is that we sum up the work element time and then we divide it by the number of workstations multiplied by the actual cycle time or the maximum workstation time. So let's go. Here we go. So we sum up the work element times, which is 1.0 divided by, this is what? The 3.
Number of workstation.
Number of workstations. And the 0.4?
Is the CA.
The CA. So eventually we have 1 divided by 1.2, which gives us 0.833. And in percentages, it is 83. Hello. It is 83.3. That is the efficiency of the line. We have achieved the maximum efficiency. There is no way we can do this better. There's no way we can do this any better than what we have done. Okay. All right. As very good and bright students, I leave you to try your hands on this. So let's draw, first of all, let's draw our precedence diagram. Everybody should try you. I beg you people, everybody should try. Are we done with the precedence diagram?
Yes.
That's where you need to start from. Six. Summation of the work element is divided by the cycle time. So 0.1 plus 0.40 plus 0.50 plus 0.20 plus 0.60 plus 0.40. All divided by all divided by 0.5. Mute yourself. 0.10 plus 0.40 plus 0.50 plus 0.20 plus 0.60 divided by 0.6, which is 3.7.
Same question.
Yes, go ahead.
I've been able to
Okay. You have done.
A is going to B and C.
A is going to B
Then
and C. Okay, correct.
Yes. Then since D is not having a president, it's standing on its own.
Yes.
Then C is going to E.
C
and
is going to
D
B.
is going to F.
No.
C.
C is going to where?
E for
E.
Eric.
Okay. Yes.
Yes. Then B is going to F.
D is going to F.
B
is going to F. Yes, correct.
Yes. Then D is going to E and is going to F.
Okay. D only goes to D only goes to E. D only goes to E.
Yes,
it doesn't go to F.
Yes, but the same line, E is also going to F, right?
Yes, E will go to F, but D will end at E.
Yes, D will end at E. Then E will go to F. That's what I have here.
So let me stop this and show this. Let me see if it will appear well for us to see. But I should have used the blackboard to do this, but I don't have a touch screen. Show video. I doubt. Is it showing?
Yes, please.
It's too close. We can't see it fully.
Is it any better?
Yes, manageable.
Aha.
Yes.
Well, I wanted to ask a question.
Please go ahead, Leonie.
If you put, no matter what you put the D, it doesn't matter, right?
It doesn't matter. So the D can be, but you see, let it flow, let it be in like from left to right kind of direction.
Yes, I put the D in the middle, like center, since it depends on nothing.
Okay, so that's fine. That's fine. But as long as you got something like this, that's too close. Yeah, you got something like this. Is it okay now?
Yes, please.
Okay. Thank you. So we are done with our precedence diagram. Once you draw your precedence diagram, the next thing is to calculate the theoretical number of workstations. How did you do that?
So you need to change the 40 hours to minutes.
Okay.
You get 2,400.
Yes.
Divided by 4,000, you get 0.6.
0.6.
Then you find the N. The N is the 0 plus 10 plus 40 plus 50 plus 20 plus 60 plus 40, and you get 2.2.
Yes.
Divided by 0.6, and you get 3.6, which is 4.
Okay, 3.6, 3.7. And that is approximately 4 workstations.
Yeah.
So our workstations 4, correct?
Yeah.
Okay. Now, what is the next thing we need to do?
Draw a table.
So we prepare a table. From what the diagram we have, workstation. So how many workstations? What? 4.
4, yeah.
Let me write that down. You are teaching me, or I don't know. So workstations.
So you write workstation.
1, 2, 3, and 4.
Then you write element.
Now we deal with elements. Elements. So which element are we assigning to workstation 1?
Workstation 1 would be A, B, and C.
B and C.
Yeah.
Hey, Krachi,
So
if you put
where is the
A, B, C.
A must be done first.
Remember precedence.
A and B, sir.
A and which one?
B.
A and B.
There's no C.
Yes.
A and B. Okay. So let's put A and B there. A and B. And A and B. A is 10, this is, so we have 0.10 remaining, eh? In terms of time remaining.
Yes, please. Yes, please.
So 10 time remaining. Two.
And the remaining element.
What station? Element C.
Element C.
Yes, please.
Which one?
What
Element
station?
C. Okay, so let's put C.
Wait.
C into workstation.
So that's for number 2, huh?
Yes.
Workstation 2, not number 2. Workstation. Use the term so we all know. We can all follow.
Station 2 is C.
So we put C there.
0.5.
What is the time remaining?
0.1.
0.1. 0.1. Then we come to work elements.
3.
Workstation 3. Sorry, workstation 3. Which ones are we putting there?
Element D.
Element what? Element what?
The D.
Element E.
Element
E.
Element E.
Why can't you put, we can't put element E because
D.
at that
It should
point
be
we
D.
have not done D.
Yes.
So let's put work element D there. So we put D there. D is 0.20. Can we add
Yes,
anything
please.
to it?
No, please. We can't add E and we can't add F because E must be done first before F.
Okay. So work element D goes into workstation 3. And what will be the time remaining?
0.4.
0.4. Now work element, workstation 4, which work elements are going in there?
E.
E and F.
No,
Now if you put E and F there,
Only E.
it's only E.
Only E.
And you see that you have
one
work. Wait, I'm coming. I intentionally allow you to work to get to a ditch. And then you can know the mistake you have done.
No.
You see that from what you have done, we have one work element remaining. We can't fix it anywhere.
Yes.
So we go back and rearrange. So the way we arranged it wasn't correct. Let's try another option. Can we do A and C together?
Yes, sir. It's possible.
Yes, please.
So we put A and C.
Yeah.
But C depends on A. So we'll do A and C together. A and C will give us how many minutes?
6.
6, exactly. So we have nothing remaining, correct?
Yes, please.
Can we do B and D together?
Yes, please. And it will also give us 0.6.
Class, do you agree?
Yes, sir.
Yes, please.
So we do B and D together in workstation 2. B and D together in workstation 2. How much time do we have remaining if we assign the 2 to workstation 2?
No, it's exhausted.
Nothing. Okay. Then, so we have signed B and D, we have signed A and C. What about, so the next one obviously would be work element E, correct?
Yes, sir.
Yes.
Yes, E.
So we put work element E into which workstation? 3. We put work element E into workstation 3. And what will be the time remaining?
0.
0. And then the last one, work element F, goes into which workstation?
4. Workstation 4.
It goes into workstation 4. How much time do we have remaining? 0.2. So when you are assigning, you need to take your time to do this. You need to take your time to do this. Okay. Now we've done the assignment. We now need to draw the assembly line diagram. So we draw the arrows and the boxes. First one is where WK1, which is workstation 1. We put A, comma C there. What is the total time for A and C?
0.6.
0.6.
0.6. Then we'll move the arrow from A and C to the next box. Next box is workstation WK2. Which work elements are there? B and what?
D.
D. What's the total time for B and D?
0.6.
0.6. Then we'll move the arrow to the next box. Which work that will be WK3, workstation 3. Which work element are in that one? Only one, eh?
Yes, please.
Yes.
Which is you. What is the total element time?
0.6.
0.6. Then we draw the arrow from that box to the next box. We now have our 4 workstations, and that will be WK4. And in that box, we'll have work element F, which takes how many minutes? 0.4 minutes. 0.4 minutes. So we are done. That is our assembly line diagram. What do we need to calculate again?
Work cycle.
SCA.
SCA.
SCA. Do we need to calculate the CA? No.
Okay,
We need to
0.6.
calculate. Eh? What do we need?
Work
I
cycle.
need to calculate the
Work cycle.
Which work cycle again?
efficiency.
The efficiency. The efficiency. Class, 1 minute. Hello, madam. Yes. Alternative Bain. Okay, still. Yeah, thank you. Okay, so we calculate the efficiency of the line. So efficiency of the line, which is capital E, is equal to summation of the work element times. Work element times, we have already summed them up to be what? 2.2, correct?
Yes, sir.
2.2. As for that one, if you have done the initial computation and it is 2.2 in your work, and you come to this point and you just put in 2.2, I'll accept. I know where it is coming from. But where you have not computed any 2.2 anywhere, and you come and tell me that 2.2, I would assume that you stole it from somewhere. Right. So it's 2.2 divided by, what is our n? Our small n?
4.
4 multiplied by, we go through our assembly line diagram and we look for the highest or the maximum workstation time. What is the maximum workstation time?
0.6.
0.6. Again, coincidentally, the maximum workstation time is the same as what?
Yes, sir.
The same as the
The same as the CD. The CD. I keep emphasizing this because today this is one area where students do make a lot of mistakes. So the CA is not the CD. Take note. Here it's just coincidental that the CA is the same as the CD. So 4 times 0.6. So the next one will be 2.2. If you multiply 4 times 0.6, what do you get?
2.4. 2.4.
2.4. And if you do the division, what do you get?
0.916.
0.916. 0.916.
Recurring.
66.
Okay, 0.9167. 0.9167. And like I said, usually the efficiency is presented in percentage. So you just move a percentage, 100 has how many zeros? It has two zeros. So we move the point where it is 0.9167. We'll move the point 2 times to the right. Yeah. And that becomes 91.67 what percent?
Yes, please.
I thought you said when it's the final answer, we can leave it at 2 decimals.
Yes, but this is the final answer, isn't it?
So if we are leaving it at 2 decimals, will it not be 0.92?
0.92.
That's not
but
the last. That's not the
no,
final.
in percentage.
Okay.
I don't know whether I understood your question.
So please, the final answer is supposed to be in percentage. And
Yes. So we have 91.67%.
Thank you.
Is that correct? Am I confusing anybody?
So we round up the percentages, not the decimals, right? I'm asking because when you do the calculation, you have 0.916 something. And if we have to round it at that point, it will be 0.92. So do we round up after we've converted into into percentage or before?
No, if you do it there, you convert it to percentages, it will be the same. So in that case, you are going to have 92%.
Yes, sir.
Well, if you write 92%, I'll give it to you. In an exams, if you write 92%, I'll give it to you. But in the quiz which you do on Sakai, I'll specifically say leave your answer in for each question where I require you to leave this thing in some decimal places, number of decimal places. I will indicate the number of decimal places that I want. Because whatever you type it in, if it's not consistent with what has already been inserted into the system, it will mark you wrong. I hope that is understood. Leonie?
Yes, sir.
Okay. So our efficiency,
question.
Yes, go ahead.
The first one, you did the work cycle, but this one you didn't calculate the work cycle.
What is a work cycle?
That's the highest number, this thing. The workstation, the one with the highest number.
The maximum, the CA. The CA, you don't work it out too. You just look at the workstation and then you see. You see that when you draw the assembly line diagram, the work element which you put into each workstation, they have their individual times required to complete them. So you sum them up. And in this our example, workstation 1, we are putting which work element? A and C, correct?
Yes, please.
And A has 0.1, C has 0.5. So if you add them, we have 0.6. And then you do the same for the 3 remaining workstations. So when you come to the calculation of the efficiency, you just look at your assembly line and you pick the maximum workstation time, which is your CA. Please, is your question answered?
Yes, please.
If you are not clear, tell me exactly where you are not clear so I can clarify.
Oh, no, I get it now.
You get it now?
Yeah.
Okay, so I have taken you through how to calculate the efficiency of the line. The last thing which you need to understand is the balance delay. Balance delay. So if I ask you to calculate the balance delay, the formula says, so balance delay, the formula says is equal to 1 minus the efficiency of the line. Yeah? So what will be our balance delay here? 1 minus 91.7 or 1 minus 92%. And that will give you what?
$0.83333. Recurring. 0.083333.
0.08. It will be 0.082. It's not 100 is 1 minus.
This is 1 minus 91.7. We get negative.
Oh, sorry. it's going to be 1 minus, what is the name? 0.9167, sorry.
And that will give us
100 minus 91.67%.
It will give us 0.
To subtract the 91.67% from 100%, and that will give you what?
8.33.
Okay, 8.33%. That is the idle time. Please note, the balance delay is the same as the idle time. So sometimes you can say, calculate the idle time on the line. Clear?
Yes, please.
Okay.
Yes, sir.
Thank you. So we are done with this for today. Let's go back to our slides. Unless there is any question that I need to solve, I need to clarify. Class, any question?
No.
Question. Okay. So the next one we are going to do is the project management. In our individual lives, some of us have handled projects before. If you not in, say, an organization, but your individual capacity. Some of you are building houses at East Legon. Others are building houses at Ajenkutuku. Others are at my estate, Ablekuma. And if you're putting up a house, it's a typical example of a project. Organizations will once a while come up with a project that will have to be executed. So we need to understand some concepts relating to the management of projects. So a project is a unique one-time operational activity or effort. It has a unique purpose. It is temporal. How do you pronounce that word? Temporary. I told you from the beginning of this the semester that I have problem with my R and L, correct?
Yes, bro.
So I hope nobody is laughing. Sadiq Ahmed, why are you laughing?
Hey. I'm not laughing.
We'll see somewhere that my lecturer couldn't pronounce the word temporally. Okay, so a project has unique purpose, temporally in nature, and draws resources from various areas of the organization. Now we are saying that a project draws resources from various areas of organization because usually when we knowledge relative to the project at hand. And we have to draw these people, pull these people from several departments within the organization. So we can have people coming from, depending on the nature of the project, we can have people coming from marketing, some from production, some from accounts, some from procurement or logistics department. And then we put them together as a project team. The project management is the management of the work to develop and implement an innovation or change in an existing operation. So what project can the company introduce? For example, the company can say that, okay, we've seen that now a lot of people want to trade with us online. So we need to introduce e-commerce. And that could be a project. the introduction of the e-commerce business model into the organization. That will be a project. They will form the team, assign the team with the role, their responsibility, their mandate, and ask them that complete this project by so and so date for us. Okay? And if we are introducing e-commerce as our new business model, that becomes an innovation. It also becomes a change. We may also decide that, okay, we've seen that the Ablekuma area is growing. Some small factories are coming up in that area, but there is and it can be handled as projects. Can be handled as projects. Now, it involves planning the project. It also involves controlling project activities. Why do you think we have to plan the project? If we don't plan, what happens? Leonie?
I think we need to plan to know the resources needed.
Yes. When we plan, we are, okay, Benjamin, your hand is up too. Ben, your hand is up. Hey, it's not Benjamin, Reginald, your hand is up.
Hello.
Hello, I'm here.
Can you hear me?
Yes, please, I can hear you.
Yeah, I think we do that so that we'll not waste resources.
Yes, we do that so that we not waste resources. We do that. So we do. Francis, your hand is up too.
Also allocate and apportion budgets to various stages.
Yeah. So planning will enable us know the specific activities to be incorporated. Planning will let us know the objective of the project. Planning will let us know the resources that are required and the people that we need to recruit into the project. Yeah? And then controlling project activities, very, very important. Why do we need to control project activities? Why do we need to control project activities?
So please come again.
You avoid possible delay and waste of resources.
To avoid possible delay and waste of resources. Your building that you people, or the building that your father was putting up at Ashoman and Ablekuma, were you people, you guys not going there to visit them? When people call you that we need 10 bags of cement, don't you ask, what are they going to use the 10 bags of cement for? Or don't you call the mason and agree with him, this week, which work are you going to do? How many bags of cement are we going to need? And it's all part of controlling the project, because if you don't control it, you decide, okay, I'm putting up a 10-bedroom facility. Then you go and buy the cement and come and heap it. In the end, they will steal it. You see? So we need to control project activities, one, to ensure that project is completed on time and project is also completed within reasonable cost. Reasonable cost. What are the elements of project management? So the key element, we need to consider a project team, which I've already mentioned, and the project team is made up of individuals from various areas and departments within a company or outside a company based on their. So sometimes if we don't have the expertise in-house, we may have to recruit somebody, a specialist from outside to come in to help us with the project. But normally the team that we constitute, the team is formed based on individual members' special skills, their expertise, their experience. Their special skills, expertise, experience relative to what? Best one.
Experience.
To the project at hand. Then. Now the job of the project manager is very key. You are central to the entire project. You need to be coordinating activities. You need to be making sure that deadlines are met. You need to be generating reports. Project manager is key to the execution of the entire project. What are the bad effects of assignment to a project team? So Bismarck belongs to the finance department. We have constituted this team to go into electronic audits. Now customers want to make their orders electronically. So that has become a team, a project for a company, and the team to manage to ensure that that project is executed. Bismarck is recruited as one of us, and he originally belongs to the finance department. Now he's a project team member. What will be the effect of assigning Bismarck to us? See, there will be temporary loss of workers and staff from their permanent department. That is when people are severed permanently from their permanent department, and they are assigned to the project until the project is completed before they come back to their departments. Then sometimes too, we can have project team members still working with the project and also be working with their department, their permanent department. So in the case of Bismarck, even though he's a team member, project team member, at the same time, he's still a key staff in the finance department. When that happens, you tend to see an employee serving two masters. Who will be the two masters here? Using Bismarck as our example, who will be the two masters here?
The finance department and also the project management.
The finance department and where?
And the project team.
Okay. I was expecting you to be a bit precise, but I'll take what you have said. The Bismarck will be reporting to the head of finance. Again, Bismarck will be reporting to the project manager. These are the two masters. And sometimes this can be worrying. Early Monday morning, finance department says that they have a meeting. Project team, we also need to know what we are doing for the week. Early Monday morning, we have meeting. So Bismarck, which one are you going to attend? You see the difficulty that sometimes comes. And this is the reason why sometimes when such projects come up, people are severed permanently from their department assigned to the project, and they find a replacement for them in their departments until the project is completed before they come back. But sometimes these very people who you are assigning to the project team are also so critical to their own department that you can't have a replacement. You can't say within that short period, say if the project is going to take about 6 months, you can't say within that 6 months, you are going to find somebody from outside to employ to come and replace him. And so they continue to work in that dual role where they serve two masters, but they manage anyway. Then we also have project planning. What goes into project planning? We clearly define the objectives of the project. We identify the project activities. We establish precedence relationships. We are coming across that word again. What is that word?
Precedence.
Precedence. So in this case, what would this involve? Establishing precedence relationships.
You can
Where are the beautiful women in my class? And they don't want to talk. Huh? Where are they? Isata.
Yes, Doc, I'm here, but I have cold.
So if you have cold, you can't answer questions, right? Okay. All right. I'll let Joyce Money bail you out. Joyce. Joyce Money,
Yes, sir.
are you all right? Your voice is a
Yes,
bit dull.
I'm all right.
Or you are doing something?
No, no, no.
It's afternoon. Don't worry yourself. It's afternoon. Okay. Do you want to answer my question?
Can you please come again, please?
I said establishing precedence relationship. What would that involve?
I'm thinking.
You have no idea. Eh?
I'm thinking.
Okay, think. Think. My cursor is not even moving. Yehovah. Class, can anybody help?
Please, I believe the precedence relationship will be.
Okay, so 2 hands are up. Oh, this cursor. Oh dear. Give me 1 minute. I need to. Oh. Okay, so the 2 hands which are up, I have Nate, Francis. Yes.
Say, it's
Go
when
ahead.
an activity cannot start until one is finished before. Example, student running the baton race with the stick. One run, the other will wait until the other one run and give the stick out. It's an example.
Okay. All right, enough. I can now see that you even like talking more than me myself. So establishing the precedence relationship simply means we knowing which activities must come before which activities. Then we also make what we call the time estimate. Each activity requires some time estimate. So we make the time estimates for them. We determine project completion time. We compare project schedule objectives, and we determine resources that are required to meet the objectives. Resources that are required to meet the objectives. Then we specify control procedures. How are we going to control the projects? And we anticipate risks. Anticipate and assess risk to the project. In every project, there will be risk. What if it rains? What if this happens? What if the bank fails us, doesn't give us the money? How are we going to continue? So we assess this risk and put measures in place to mitigate them. Okay. Then we have something we call the work breakdown structure, which is the WBS. Now, the WBS is a tool used for project planning and organizes the work to be done on a project. In a WBS, a project is broken down into 8 major components. We break the project down into 8 major components, or the key activities required to get the project executed. And then we further break each major component into activities, and finally, individual tasks. What is the advantage of the WBS? It's a good way to identify specific activities, determine individual tasks, modules, workloads, and resources required. It also helps in identifying relationships between modules and activities, and identifies unnecessary duplication of activities. Once we have the work breakdown structure, we are able to know that this work is already being done by somebody, and we don't assign that same work to somebody else. So this is a typical example of a work breakdown structure. In this example, the projects being executed by the company is a computerized order processing system. Now the company wants to move away from their manual order processing system to a computerized order processing system. So This is what they have done, the project team has done, broken it into three major components: hardware, software, stroke system, and personnel. And with hardware, look at what they are doing. They are doing installation, they are doing testing, they are doing final testing. And installation, they are looking at this: wiring, connection, testing, they are doing connections, wiring, servers, monitors. In personnel, they are looking at recruiting, job training, orientation. In recruiting, what activities fall under recruiting? They are looking at interviews, they are looking at testing. So maybe after passing the interview, you also come and write a test so that we can screen the chaff out of the list. Then job training, where we provide individual training, we provide group training. We also take them through software and hardware. So this is a typical example of a work breakdown structure. With this, we are able to know, identify the specific job, the key jobs within the project, and the breakdown of those job activities. That's why the name says work breakdown structure. Okay? And with that, we're able to tell how many people we need with each of them. The first one is this one. So if we pick this one, we are saying that we need 3 people here, we need 1 person here, we need 1 person here. The resources, human resources that are required, we put all of them in there. Makes the job simple. Responsibility assignment makes the job simple, clearer for everybody. Project control, the primary focus of project control is maintaining the project schedule. Maintaining the project schedule means that we want to ensure that we complete the project on time. What is the danger if we go beyond project completion time? Class, anybody?
High cost. Extra cost.
That would be
increases
extra
cost.
It increases cost of the project. We might also, some contracts, if we are doing this project for a company on contract, we might also have to pay some penalties if we don't meet the project completion deadline.
Yes.
So the government of Ghana says that, hey, next year is elections. I need all my students, all my SHS students to get into universities. And they have signed up contracts with contractors. We're expanding the facilities in the infrastructure in the universities so they can accommodate all the students that are coming from so and so. They would make sure that if you don't meet the deadline, you pay a penalty. See. So that's one of the things. So key elements of project control are, we look at time management, we look at cost management. Lengthen upon Stephen, your hand is up.
Yes, sir. I wanted to ask a little question. As you were
Please
saying, imagine like Ghana, for example, maybe you can give a contract to a road contract to a contractor, like what the politicians do. I don't know, you see that maybe they will pause on the way and it will take about maybe 2 years to even complete. Is it that maybe they didn't give them limited time, or why?
Okay, so the challenge we have there is that the contract we sign with the contractors, we tell them that you up to a certain stage, you prepare a certificate. The certificate is certified. Then the government pays you. Now, when you receive that money, you continue with the project. You get to another level, you prepare a certificate. You submit the certificate. It is approved by the the consultant on the project. Then you are paid. Oftentimes, the challenge is that the contractors will raise the certificate and submit. It gets there and it never gets paid because the government may also be handicapped. There is no money. And then the project is stalled for a number of years. And the contractor wouldn't also want to complete with his money because that is the agreement in the contract.
Okay.
Is your question answered?
Yeah.
This is the reason why most of our road projects delay. This is the reason why most of our road projects, like not just the road projects, even infrastructure, I mean like school projects. It's gotten to a stage where he needs to be paid to be able to continue. He raises the certificate for payment and the money doesn't come. Okay.
Thank you, sir.
Okay. So key elements of project control are time management. We need to control time. Why should we control time? So we can complete a project on time. Why should we control costs? So we are able to, we don't waste unnecessary resources. And now we are able to work within our budgetary constraints. Then quality management. Why should we control quality? We need to ensure that whatever tasks which are to be executed on a project, people do it in a way expected. People do it to meet the standards expected. So if it's construction, we need to construct the building or the facility to the standard expected. And then overall performance management. Okay. So let's pick them one after the other. Time management, we monitor individual activity schedules and we make frequent updates. Yeah, shifting resources to critical activities. Sometimes when we see that, we'll get to know what a critical activity is in project. But before we get there, let me introduce you to the concept. A critical activity in a project is an activity that if we delay on the assigned completion time, it is going to lead on to the delay in completing the project. Any delay in the activity time will have a consequential effect on the project, overall project completion time. So for critical activities, we don't want to delay on them. So when we are monitoring time management, if we see that a critical activity is delaying, we might decide, okay, why don't we shift resources? And sometimes in construction, where some of these things are there, critical activities, you see that even in the night, they'll put on a floodlight and you see them working because they want to make sure that they meet deadlines. They want to make sure that they meet deadlines. So they make those frequent updates where we need to shift resources from other activities which will not be critical. We'll shift those resources to go and complete an activity which is critical. Then we come to cost management. Yeah, this is also closely tied to time because when the work is delayed, it increases cost. And delayed schedule will increase costs, as I have already said. As the project progresses, some cost estimate may also prove to be unrealistic or erroneous, and we may have to revise those costs as well and update our cost schedules. Okay. Quality management. We monitor projects for quality and improvements. Tasks and activities must be monitored to ensure work is done correctly and according to plan. And finally, performance management. Monitoring a project and developing time status reports to make sure that goals are being met and the plan is being followed. And we are actually following the project schedule. Yeah, and that we are not deviating from our costs. We are not deviating. We are not doing cost overruns. We are not deviating from our time schedule. All these things go into overall performance management. Okay, so now we start looking at the tools that we can apply when it comes to project management. And one of these tools is Gantt chart. Why do we call that chart Gantt chart? We call it Gantt chart because the person who first developed it is called Gantt. Google for the full name of this person. Something Gantt. What's the full name? Nanaya Edu, are you there?
Yes, I'm here, sir.
Do you want to check for me?
Sir, please, I'm porting my phone, so if I use it will go off my internet.
Henry.
Yes, sir.
It's called Henry Gantt.
Henry Gantt.
Okay, okay, great. So we named it after him. Yes, Gantt chart. It's one of the project scheduling tools. Project scheduling, so we use a Gantt chart to say that, okay, so these are the list of activities within the project. These are the times within which the project will be, each activity within the project can be completed. The Gantt chart is a graph or a bar chart with a bar for each project activity that shows the passage of time. I'll show you an example shortly. And it provides a visual display of the project schedule, indicating the start and completion times for activities. Again, it also shows our almighty precedence relationships between the activities. But we must emphasize that the Gantt chart is only suitable for small projects. Small projects will have fewer activities, and therefore the Gantt chart is able to accommodate them. But where in complex projects, we cannot use the Gantt chart to provide an adequate visual display of the project schedule and project activities. Take note. That's why that's the point here. Suitable for small projects with relatively few activities and precedence relationships. Okay. So the table below shows activities in a building project. The Gantt chart can be used to provide a visual display of the projects. So this is what we have: activity, design house, obtain financing, we lay foundation, which will take us 2 months. We order, we receive materials, which will take us 1 month. We build the house, which will take 3 months. We select paints, 1 month. We select carpet, 1 month. We finish the house, 1 month. Class, let's have a discussion here. Looking at these activities, do you think some activities can be done concurrently? You think some activities can be done concurrently?
Yes.
Which activities?
Select paint and select carpet.
Selecting paint, selecting carpets, right? I know you have the lecture notes. Don't look into it. I want the lecture note is yours. After class, you can look at it. Let's have that discussion. Try and force your brain to think. Okay. Can we combine designing the house, obtaining financing, and laying the foundation? Can we combine it to start at the same time?
No.
No, sir.
No.
The lady who said no, why no?
Because you need to know the design and know if you have the finance before you start laying the foundation.
Yes, because if you don't have the design completed, how are you going to lay the foundation? How are you going to dig the foundation before you even lay? It is the design that will let us dig the foundation and lay. Again, even if the design is made and we have not obtained the financing, people who will dig the foundation, I think people like Theophilus, when they come and dig the foundation for you, they are NGOs.
On credit.
You do it on credit when you want it.
For credit, come tomorrow.
I saw a hand up. Who is that?
It's me, sir.
Equia.
I was going to say the design will even determine the sort of financing you should try to obtain.
Excellent, excellent, excellent. So what I am trying to point out here is that when we draw our network diagram, in balancing the assembly line, that diagram, what is the name? We call that the precedence diagram. Yeah. Over here, we call it the network diagram. We call it the network diagram. Okay. Let's take a look at the network diagram. Sorry, the Gantt chart. So designing the house. How many months?
2.5 months.
3 months.
It's not 2.5, it's 3.
3, yeah, 3.
Yes, it's 3. And when we have finished with that, laying foundation can start. So laying foundation starts in the 3rd month and finishes in the 5th month. That is when building the house itself can also start. And building the house starts in month 5 and finishes in month 8. From then, finishing the work can also come in 1 month, and we finish the whole project in 9 months. Class, take a look at this visual display provided by the Gantt chart and tell me all the possible information that if you take a look at this, you are able to get. Christian Sappho, what do you get? What information do you get from this diagram? This chart. You were sleeping.
No, Doctor, I'm
My
not sleeping.
instinct tells me.
No, I'm even in class.
My instinct tells me you were not paying attention. That's why I just mentioned your name. Okay, Bismarck, let's go. But Christian Sappho, some things you don't need to think about it. You take a look at, I mean, sometimes you people you amaze me. Just take a look at this diagram and tell me one information that you get from this diagram. You can't tell me anything and you are not thinking. You're a master student too. You are not an undergrad. Okay, 2 hands are up.
From the chart, you can see that you have to design the
TMO?
From the diagram, I realized that designing the house and building a house takes the maximum time. It takes much of the time of the project.
Okay, so that's one information you get. Okay, so you get activities that you get to know the duration of all the activities. Okay, what other information do you get? Leonie?
I also get that you can concurrently lay foundations and other materials at the same time.
So you get the information that some project activities can be done concurrently, correct?
Yes, sir.
Okay. What other information do we get? I have another hand up. Michael Emisa, Michael.
Okay, so you can also finish the house within a 9-month frame.
Okay, so you also get this information. You get the project completion time. That's what you also get from this visual display. Yeah, Christian Sappho, can you now talk?
Yes, Doc. Doc, I can.
What can you see?
You can build a house and at the same time you select a paint concurrently.
That information is already given, that some activities can be done concurrently. What other thing do you see? Don't give me that undergraduate answer. Say I see nothing.
Okay, Doc. So I can also see that you can also select the paints.
You can also select the paints. And what?
All right, so you can build a house and then also select a carpet also.
All right. Gifty?
Hello, sir.
Gifty, yes.
Yes, please. I think I can also see the fact that from start to finish of the project can take about, say, 9 months.
9 months. Project completion time. Project completion time. This is so obvious, but nobody saw this. So, Christian Sappho.
So please,
you see where my this cursor is hovering? What can you see?
The
project activities is so obvious, but you all missed it up. Louis, what can you see?
So that's what I was about to say. You get to know where to start and where to finish. The projects that you need to do, the precedence.
Thank you. Thank you. And you also get to know, as for this one, I know is a bit technical, because this is your first time, you may not identify it. We also get to know the critical projects. The critical projects are projects that whose duration we cannot go beyond. The moment we go beyond that, we are going to exceed the project completion time. And can anybody identify some of those critical activities in what we have here? Yes. Michael, let me say your hand is up.
Okay, so I think the first one, design house and obtain financing.
Design
the moment
house.
we exceed it, we can't start with the laying of the foundation.
Aha. So you see, if we exceed this activity by say 1 month to the 4th month, then it means this activity, laying the foundation, will start in the 4th month. Then it means building the house will also have to delay. And it means finishing the house will also delay. In the same way, if we meet the line, the deadline for this, meet the deadline for this, and we delay this, this is also going to delay. These are usually the critical activities, activities whose duration we cannot go beyond. Delay on it for how many months? This one.
For one month.
We can delay on it for 1 month and nothing will happen to the project completion time. The same thing with this activity. The same thing with this activity. In fact, even with this, we can delay this activity for about 2 months and nothing will happen. You see. So it's important for you to identify these, and those activities that we can afford some delay on, we call them non-critical activities. Non-critical activities. Anyway, this Gantt chart will not present a good picture. As we move on, you understand the concepts better. Okay. Okay, so in project management, we used the CPM and then the PERT. CPM stands for the critical path method, whilst the PERT stands for the program evaluation and review technique. And they are all derivatives of the Gantt chart. What does that mean? If we say they are derivatives of the Gantt chart. CPM's report shows the network of activities with precedence relationship in the project. And network provides a better picture than the Gantt chart. The network provides better picture than the Gantt chart, particularly for complex project or project with many activities, CPM is a popular technique for project planners and managers. And we'll look at the AOA, activity on arrow, and the AON, activity on node techniques for project network diagram. We'll look at it shortly. Okay, so let's try and see if we can differentiate the CPM from the PERT. CPM versus PERT. Originally, these were two primary, there are two primary differences between the CPM and the PERT. Now the CPM has a single estimate for time activity. In CPM, we have a single estimate for time activity. In that, the understanding is that with CPM, we think that the time required to complete an activity is certain. So time here is treated as deterministic. We know that for sure, but that is not the case with PERT. With PERT, it makes provision for variations in the time. So for each project activity, unlike CPM, that will have a single time estimate, in PERT, we have 3 different time estimates, the optimistic estimates. How quick or the quickest time we can complete the activity. That will be the optimistic activity. Then we have the most likely time, which would be the time that if we are repeating the activity, it will normally be completed within. Then we have the pessimistic time, where we assume that if everything goes wrong, if everything delays, how long is it going to take us to complete this activity? So in PERT, there are 3 time estimates: the optimistic time, the most likely time, and then the pessimistic time. So 3 time differences. In CPM, just 1 time estimate. Okay? In PERT, activities are represented by arrowed lines between nodes or circles, and that is the activity on arrow. Activities are represented by arrowed lines between nodes or circles. And in CPM, activities are represented as the nodes or the circles. Maybe in order not to confuse you, this is what we call a node. This is a node. This is a node. This is called a branch. This is the arrow. In CPM, the activity is represented on the arrow. Sorry, in PERT, the activity is represented on the arrow. In CPM, the activity is represented on the node. On the node. And so in CPM, we have activity on node. So when you see AON, activity on node, we are referring to CPM. When you see AOA, activity on arrow, it is the PERT, the PERT. And the activity here, we are simply referring to a project activity, Okay. So a node cannot be reached until all activities leading to it are completed. So going back, this node cannot be reached until all these activities have been completed before we get to this point. That's what we are saying here. No activity can start until its tail node is reached. These are important rules. A node cannot be reached until all activities leading to it are completed. No activity can start until its tail node is reached. So now let's look at the critical path method. A network path is a sequence of connected nodes that leads from start node to the finish node. A network may have several paths. Yeah? Let me take you here. Leonie, if you are here, if you are starting from here and you want to end here, let's see the paths that you can take to get to 7. Let's see how many paths are there. Leonie, let's go.
From 1. You go to 2. You can either use 2 to 4 or 2 to 5.
No, so just mention the path 1, then you go to path 2, then path 3, and path 4, 5, 6.
Okay, path 1, path 2, path 4, path 7.
No. So path 1, where are you going to pass?
I'm going to pass
1, 2, 3, 4. Then you are at 7.
Yes.
So path 2, where are you going to pass? Path 2, where are you going to pass?
Part 2, I'll definitely start from, and I'm confused.
You are starting from here.
Yeah, I'll start from there. And I'm going to choose.
I think you don't understand the question.
Yes,
Does anybody understand my question?
Confused.
We are here. And we want to
part
get to here. How many routes? How many routes are there for us to?
I see 4.
You see 4. Okay. Tell me the first one.
Path 1 is 2.
You move from here.
From 1 to 2, 2 to 4, 4 to 7. Then
Okay,
path
that's
2.
the first part. Then the second part.
1 to 3.
1 to 2.
No, 1 to 3.
Okay, 1 to 3.
3 to 5.
Yes, 1 to 3. I'm there.
3 to 5.
3 to 5.
5 to 6.
5 to 6.
Then 6 to 7.
Then 6 to 7. We have 2 paths now. Do we have any more?
Yes.
Yes, please.
Yes, please.
What is it?
Then 1 to 3. 3 to 4.
1 to 3.
3 to 4. 4 to 7.
4 to 7. So that's another path. Do we have any more left?
Yes, please.
Which one?
1 to 2. 2 to 5. 5 to 6. 6 to 7.
1 to 2.
2 to 5.
1 to 2. 2 to 5.
2 to
5 to 6. 6 to 7. So that is what we mean by paths. There are several paths. Let's go back. So a network path, and because we are looking at the critical path concept, we need to know what our network path is. A network path is a sequence of connected nodes. As we just saw, it's a sequence of connected nodes that leads from the start node to the finish node. So this is the start node, this is the finish node. So the sequence of nodes. Okay. Now a network may have several paths. And in the example we've just seen, we have 4 paths. The longest path in the network determines the total time required to complete the project. And this is the critical path. Now, please read this. Let's all read this. The longest path in the network determines the total time required to complete the project. This is the critical path. Let's go back to this diagram. Now, this is the activity. The top is the activity. The top number is the activity. Below is the duration of the activity, and it's in months. So this is activity 1, which will take 3 months. This is activity 2, which will take 2 months. This is activity 4, which will take 3 months. This is activity 7, which will take 1 month. List the network paths. So write 1, then you put an arrow between it to 2, put an arrow between it to 4 to 7, and sum up the duration. Let's see how many paths you are going to get. Let's get the duration of each path quickly. Do that for me. I know my time is almost up. I thought I could reach 270 today. Hey. This is our lecture 8, or lecture 7? Lecture 8. Are you done? Are you done? If I ask you to do something, please do.
Yes, please, Brini, but I don't know if I should sum up the durations in each node.
Yes, for every path you have identified, and I think we've done that already. So we have one of the paths we 1, 2, 1, 2, 4, 7. Then under them you have the duration 3, 2, 3, 1. So sum the 3, 2, 3, 1 up for me. I'm interested in all of them.
The first part is 9.
The first one is what?
The first part is 9.
9.
And the second is 8.
The second is 8.
And the third is 7. And the fourth is 8.
Okay. Class, did you all get that?
Yes, sir.
Okay. Okay, thank you. So the longest one is 9, correct?
Yes, sir.
Yes, please.
Yes.
And that is what we are referring to as our critical path. You see? The longest path in the network determines the total time required to complete the project. And you see that when we had a look in the Gantt chart, it was 9 months. When we did this one too, we collected a duration of the activities. We had the longest to be 9. So that path is our critical path. And the duration there is the minimum time required to complete the project. So the project can only be completed within minimum of 9 months. You can't do it less than that. Okay. And all the activities sitting down on the critical path, from what you did, which activities are sitting down on that, the one that gave you the 9 months, which activities?
We have the design.
Mention the activity number.
1,
2,
4,
4,
and 7.
And 7. These activities sitting down on that path are called critical activities. Technique, activity on node. Remember we said that in PERT, activities are represented on the arrow. So that's what we have here. Activity 1, we designed the house, which is 3 months. Activity 2, we lay the foundation. Activity 3, we order and we receive materials. But in PERT, you see, this arrow goes here to 3. And this one goes here. We need this one to come and join here, but this is not an activity in reality. So we call this a dummy activity. And dummy activities are activities in project which doesn't exist in reality, and therefore they don't consume resources. Dummy activities don't consume resources. As you can see, it is 0 time. It is not taking any time. And normally we represent dummy activities with dotted lines. We just need it to connect to this so we can see the flow of activities. Okay? And this is how we usually do the network diagram in PERTs. We need to be able to differentiate this from the regular one we do in CPM. Okay? And in CPM, this is what we have. We have gone through this already. This is what we have. This is the activity on node. So the activities are represented in the node. The circle is the node, and activities are represented in the node as we can see. Okay, what we just did is here. Our part 1 was activity 1, activity 2, activity 4, activity 7. If you sum up, their duration is 9 months. If you come to part B, activity 1, 2, 5, 6, 7. Sum up, their duration is 8. Activity part C is 1, 3, activities 1, 3, 4, 7. Sum of their duration gives you 8 months. Activity D is 1, 3, 5, 6, 7. Sum of their duration you have 7 months. So the longest out of these paths is path A, which comprises of activities 1, 2, 4, and 7. And now this is the minimum number of months required to complete this project. Remember, the longest part represent the minimum time required to complete the project. And that path also becomes, the longest path also becomes the critical path. And activities that sit on that path are called critical activities. Okay, time is up. It's already 1 o'clock. Gifty, note this figure down, 265 down. And we'll try and finish up next week with project. Class, before we end, up to this point, any question? Okay, no question. Francis, your hand is up. Please ask your question. Francis Nathan.
Sir, prior to the notes, is there a special?
No. I mean, we don't need you to, I mean, your ability to identify, you can label them anyhow, but no matter what you name them, it will still have these figures. Okay?
And
go
use
you can name them
and put the last specific rule guiding like.
Yes. What we need to know is that one path consists of these activities. Another path consists of these activities. That's it. It doesn't have to follow any sequential order. The way you see it, you list them. Understood? Okay. So, hello. Basically, we can't hear you, but if you can hear us and you can type your question, that would be nice. Yes.
No, please, talking about the format of the
I think he needs clarity on the format for the IA. That's if I got him right.
The format for the IA.
Yes, I think that's what Bismarck wants.
If that's the question he wants to ask, the format for the IA is going to be on Sakai. On Sakai, what I've done is I've built multiple choice questions there. And for the multiple choice, the value is 1. If you get 1 correct, you get 1 point. Then in addition to the multiple choice, I have questions that you need to calculate and then type in the figures. Okay, so when you are ready to take the quiz, have an exercise book in front of you so that you can do the calculations. You need to do the calculation. In fact, I can ask you to, I can put 2 process before you and ask you to tell me what will be the cost of process 1. So you need to do the computation and put in the cost of process 1 into the system. So you any other question?
There's someone is also asking what time.
What time for what?
The IA. Someone is also asking.
so that you have an idea what it will look like. Is that okay?
Yes, sir.
Some of you didn't take the assignment serious at all, to the extent that somebody only did one question and submitted it for me to mark. I was just surprised. Did only one question, submitted it for me to mark, but I've also marked it and given the person the score he deserves. I don't know whether it's the regular students or the weekend student, but that's one of the cases I came across. So when you are going to take the IA, take it serious, because they are all going to work together to give you your final score. The weekend students, I asked them to take the trial quiz, and lots of them scored 0. I was surprised. Lots of them scored 0. So I'll do the same thing to you. I'll give you the trial quiz. Try your hands on it. It is not recorded. Try your hands on it so you know what is actually coming. Okay? Thank you very much. Any other question, class? No question. In the absence of any further question, let me take my, hang on, don't hang up yet. I told you I'm going to record class attendance. Where is it? Let me take my class attendance first. Four. Screen. Okay. So class, I'm done. Thank you very much for your time today. I've taken my attendance. I know how to do with it.
Thank you, sir.
Okay.